In this problem, we're given a poset A, which is ordered with the division relation, and this set A is 2, 3, 5, 6, 8, etc. I mean, these numbers, right? They are related, as I said, with this division relation, which is an order relation, a partial order relation. We have to draw the Hasse diagram of this poset, and then find a topological order that contains the partial order. Remember that the topological order is a total order, a linear order, that contains or subsumes this partial order, right? Okay, so let's go for the first, right? Remember, in order to do a Hasse diagram, it's a good idea to find the minimals of the set, then remove them, then find the minimals of the remaining set, etc. So in this case, the minimals of these sets are, of course, the elements that are not divisible by any other in this set, right? And you can see that 2 is one of them, right? 3 is another one, 5 is another one, and this is because they are prime numbers. 6 is divisible by 3, 8 by 2, well, every even number is divisible by 2, and then 15 is divisible by 3 and 5. So these are the only minimals of this set. So the first layer of the Hasse diagram will contain these 3 numbers, which we are going to draw in this order, just because, well, I mean, you can put them in any order that you like, just at the same level, and this is because it's going to be less messy, the diagram, if you do it this way. Okay, now once you remove them, you're left with the set 6, 8, 10, 15, 80, and 90. And now you look for the elements that are not divisible by any other in the set, right? 6 is one of them, of course. 8 is another one because it's not divisible by 6. 10 is not divisible by any of them, right? Now 15 is not divisible either. But then these two are divisible by 10, so these are excluded. So this is the new layer of minimals. So again, I'm going to draw them like this. This is going to be 10, right? Then I'm going to put here 8. Okay. So this is 8. And then 6 is going to be here. Finally, 15 is going to be here. And now we link the relations that we find. Of course, 2 divides 10 and 8. That's the reason we put them together, and also divide 6. Right? So we have this. Now 5 divides 10. So we have this line here. And divides 15. Okay, so we have these 2 lines. And 3 divides 6 and divides 15. These are all relations that we have. Okay. Right. Now you remove this the previous minimals, and we're left with 80 and 90, and they are not divisible by each other, so both are minimal. So these are the last elements in the list. So we have here 80, right? And here we have 90. Okay. Now 10 divides 80, of course, and 8 divides 80, right? 10 also divides 90. Okay. 6 divides 90, and 15 divides 90. Okay, so this is the Hasse diagram. So this represents all possible orders here. You can see that if you go to a bottom element, let's say the 5, and for instance take the 90, well, 5 is the divisor of 90, but as you can see, there is a line joining 5 and 90, and increasing, a line that always goes up, right? Okay, and same for the other elements. So you have 3 here, and there's a line that joins 3 with 90 because 3 divides 90, but there's no line going always increasing, always going up, that joins 3 with 80 because 3 does not divide 80. Okay, so this is the Hasse diagram. And of course, for the total order, what you can do is just take the standard order, the standard order of the natural numbers, this one. So we can say that 2 is more than 3, is more than 5. Like this. And the reason this order subsumes the other one is because if m divides n, then m is smaller than or equal to n, always, right? So this order is compatible with this one, and it's a total order. So this is a topological order. It's not the only one. You can find all sorts of orders, but this is like natural, so why not using this one, right? Okay.